So you should be familiar with exponential functions and their properties. So these are very traditional ones that we would do in Algebra 1 and then Algebra 2. One of the things that you're going to have to be able to remember though is they go backwards and forwards. And I know we talk about that a lot in Algebra 2. But a lot of times it's, okay, so if I see this or maybe this, you write it this way. But you also have to be able to see this if there's subtraction in the exponent to rewrite them out as division. Or here, anything to the 0 is 1. So if I tell you something is 1, well, you can give that any kind of base and then work with it that way. So just remembering those exponent properties. And then also remember the natural base e. This is a real world application base, which is going to then go into natural logs. We do it with compounding interest. There's lots of just different real world scenarios that deal with e. But e is called Euler's number, and it's approximately equal to 2.718. It's on your calculator. It's on the left-hand side right along the natural log button. Okay, so now we're going to get into solving exponential equations. And you've seen these types of problems before. Nothing out of the ordinary. Here, if I don't have a calculator, I can easily do this by equating like bases. So 27 is equivalent to 3 to the third. So since their bases are the same, then their exponents have to be equal, and now you can solve. And you can always check it. Put 2 in here, or I'm sorry, put 1 in for x, so 3 to the 1 plus 2, so 3 to the third, that's 27, so it works. Don't forget to check those answers. And then the same thing for b. Why don't you pause it and try this one on your own. So 4 is equivalent to 2 squared to the 2x plus 1 power, and 8 is equivalent to 2 cubed to the x plus 2 power. And again, remember power to power we multiply. So my bases are the same, therefore I have to multiply my exponents. That's 4x plus 2. That has to equal 3x plus 6. So subtract the 3x over, subtract the 2 over, x therefore is 4. Okay, so just going through, making sure that you're comfortable solving exponential equations without our calculator. And then we're going to learn how to do it with our calculator as well once we get into logs. Additionally, being able to graph exponential functions. Remember, an exponential function is y equals b to the x. So some base to the x value. And then we'll look at some transformations as well. So without using your calculator, graph each of these on this axis. What I recommend is doing them in different colors. That way you can see all of the different parents based on what the base is. So graph a few points for this one, graph a few for this one, and graph a few for this one. Again, doing each function in a different color. And then also don't forget about your horizontal asymptote. So pause now. So here are each of the 3. I did each of them in a different color. So they all have a different parent function. So what's important to know is when we start doing transformations with these, we know that whatever our b value is changes what our parent function is, and then we'll be doing all of the other transformations with them. So this piece here is going to get you into figuring out what parameter does what in the exponential function. So feel free to plug in values for a and see what exactly it does. Pause this, try a few things, and then I'll go through each of them just to make sure that you have them. So if there's an a in the front, that's actually affecting your y value. That is a vertical stretch or compression. Also called a dilation from geometry. Whereas here the a is up top with the x. So this is physically attached to x. That's going to make a horizontal stretch or compression. We don't do a lot of horizontals in a lot of our different functions. The only one that we really worked on it with was trigonometry in your previous classes. But here we could have that multiplier up there and just know what it does. Since it's directly attached to x, it's the opposite. So if it's a 2, it's a compression, and if it's a half, it's a stretch. Because again, whenever it's affecting your x, it's that opposite operation. This one here, this b is outside here, so that is a vertical shift. This is adding onto your x value, so that's a horizontal shift. A negative attached to your x value, so it's changed the negativity of x. So if I had a positive x here, it becomes a negative x. Or if I had a negative x here, it becomes a positive x. So it takes the opposite of your x value, which means this is a reflection over the y-axis, because it's flipping the sides of your y-axis. Versus here, this negative is down below, which means it's affecting your y. Therefore, it's a reflection over the x-axis. Because if that's the case, then I have a value up here, we change its negativity, it goes down here and vice versa. So that's reflecting over the x-axis. So what we're going to do is we're going to put these together and we're going to figure out what kind of transformations we have. So we have this function. Keep in mind, one of the things that hopefully you noticed is every one of these three graphs had a horizontal asymptote at y equals 0, and it also contained the point 0, 1. So those were two things, no matter what our base is, those two things held true. So the same thing's going to happen here. So first thing that we should notice is what kind of transformations we're having. First off, it's y equals 2 to the x, but then it says plus 3. With this plus 3, it's outside, which means it affects your y. Since it affects your y, it's shifting things up and down. Y is your up and down. So therefore, everything moves up 3 spots, which means there is a horizontal asymptote at x equals 3. And then the other thing that we always have is we have this point up here at, well, it was here at 0, 1. That point shifts up 3 spots, so that's right here. And then we had the point 1, so 2 to the first power is 2, so it was 1, 2. So therefore, from my asymptote, it goes 1 over and 2 up. And then if I put 2 in, 2 to the fourth, or 2 to the second is 4, so it'd go 2 over and 4 up. So again, from that asymptote, it goes 2 over and 1, 2, 3, 4 up. And I get this graph. So y-intercept, as we said before, it was at 0, 1, that shifted up. So therefore my y-intercept, x is 0, y therefore is 4. And we can figure that out by plugging that in here. Put 0 in for x. So what's 2 to the 0? 1 plus 3 is 4. So then the equation for the asymptote, so this is part 1. My asymptote, since it is a horizontal line and it's shifted up 3 units, that's a y equals 3. Domain, all real numbers. X is an element of the reals. And then my range, it has to be from here up. Therefore, it starts but excludes -3 and goes up to infinity. I sketched the graph already. And then what you can do is you can use your calculator to figure out where this, so this graph here, intersects with this. So go ahead and put that into your graphing calculator and do an intersection. And since we're looking at the intersection, we're looking at our x values. I've got to find the x point of my intersection. So x therefore equals -0.4895, etc. So rounded correctly is -0.490. Make sure you include that 0 there. So the first 3 parts should be able to be done without a calculator. You would not get your calculator on this type of a problem. Obviously, the last part you would have to have your calculator for that, unless I give you some other kind of easy number that you can solve for. So continuing with exponential functions, we have story problems. We've looked a little bit at story problems, but we're going to keep going with these because these types of story problems come up often. We have a value of our boat in pounds, modeled by the function as follows, where x is the number of years since the boat was manufactured. So find the value of the boat when it was brand new. So x, look at how it's defined. The number of years since the boat was manufactured, which means if I want to figure out when it was brand new, I would know that my x value is 0. So y equals 20 times 0.85 to the 0 power. And of course, you know 0.85 to the 0 is 1. Therefore, it was 20 in thousands of pounds. So if we're going to figure out what the value of the boat is in 3 years, so now this is going to be 3 years later, so y equals 20 times 0.85 to the third. So I can go ahead and type that into my calculator, and I get 12.2825. Now remember, this is in thousands. So if I write this out exactly as my exact answer, oops, it's not dollars, it's pounds. So if I write out this value exactly, that's 12282. So 1,282.5 pounds. And that's exact. Okay, if we were rounding to 3 decimal places, that wouldn't to 3 significant figures, that wouldn't necessarily make sense, and we'd lose that 82.5 pounds. We have an exact answer, give your answer, and it's an exact answer. And the last one, use your graphing calculator to estimate the value of the boat will be worth half its original value. So now we want to see when is it half its original value. So since it started out at 20,000 pounds, I need to figure out when is it half its value, 10,000 pounds. Now, since we haven't learned how to solve when our exponents are unknown, what we're going to do is we're going to put this into our calculator. So again, that's why it says use your graphing calculator, and we're going to find a point of intersection. So into my calculator, I'm going to put this equation, and I'm going to put this equation, and I'm going to intersect them. And when I do that, I get my x value to be, so my x value is 4.265. So 3 significant figures would be 4.27 years. And your boat isn't just all of a sudden at the end of the year going to reach a value. So that's why we can have a decimal approximation with this, because our boat is changing over time. Okay, so it'll take about this many years for it to be that value. Okay. So hopefully you're getting comfortable. Oops, wrong page. Hopefully you're getting comfortable with working with exponential functions, because then we're going to move into log functions as well.